plenty of practice in the chapter for you to read on that. Okay? So we talked about saturated hydrocarbons having all the possible H's, as many H's as they could possibly hold. So all of carbon's valences are essentially filled up with maximum H's. Unsaturated hydrocarbons do not have the maximum number of hydrogens because of either double bonds or triple bonds. Okay? If we have a CC single bond and change that to a double bond, we have to remove two H's in order to have room for that extra covalent bond there. Okay? So alkenes have at least one double bond. Alkynes have at least one triple bond. So let's start with the simplest alkene, which is ethene. And at this point, we have to go by a couple of different naming systems. We're going to focus mostly on the systematic name. IUPAC is the International Union of Pure and Applied Chemistry. They come up with the naming rules. They were in the news over the break because they approved 3 new elements becoming official. So that's the same governing body that does that sort of stuff. So they have this naming scheme, but there are also many common names that have been in use before IUPAC made these rules. So ethene is the 2-carbon double-bonded compound, but ethylene is a common name that's been around for hundreds of years and is still pretty widely used. Okay? So when you are giving an answer, you should always pretty much give the IUPAC name, unless you're told otherwise. But you should be able to recognize those common names as well, if that makes sense. Okay? So that's ethene. And notice its formula is C2H4. We have a different formula. Now it's just CnH2n. Okay? As long as we have one of those double bonds, we've sort of removed that +2. Okay? And now every carbon just has 2 H's on it. Propene, right? F, remember it went meth, eth, prop, bute for 1, 2, 3, and 4. So propene has how many carbons? Yeah, it has 3 carbons. So meth, eth, prop, bute. Okay, so let's draw 3 carbons, and one of those will be double bonded. Okay, we're only going to focus on having a single, on having just one double or triple bond. Okay, there are ways to make the naming to make multiple, but we're just going to keep it simple. Okay, so propene is like that. So this carbon will have 2 H's. This middle carbon then will have how many H's on it? Yeah, it'll have just 1. And this one over in the end, that's a CH3. Okay, so really, the shape would actually be better if we did it like that because of the trigonal planar shape. This central carbon really should be trigonal planar, so it's a little better shape. Okay. We can draw the line structure for double bonded compounds pretty much just like that. You're pretty much drawing the double bond and the single bond. Okay? And the carbons, again, are assumed to be at the ends and the joints, but just now we draw a double bond for one of them instead of single bond. Okay? Now, once we get to butene, we've got a lot of possibilities. So these are all isomers, meaning they have all the same number of atoms, but they're connected together differently. So we've got 1-butene, cis-2-butene, and trans-2-butene. So in a double-bonded compound, that number indicates where the double bond starts. So if we draw this structure, 1-butene is going to have its double bond be between carbon 1 and carbon 2. So it's the lower numbered carbon that's involved in the double bond. So think of it as where the double bond starts. Okay? So that's the line structure of 1-butene. So it's going to have the double bond on the end of the molecule. Okay? And then the other ones after that are going to be single bonds. Okay? So that's 1-butene. So what does that 2-butene mean? What two carbons are going to be double bonded in 2-butene? 2 and 3. Okay. Now, cis and trans have to do a little bit with the geometry of that. So what we're going to do is we're going to draw the double bond. Okay. And then here, I'm going to draw CH3 down, H up, CH3 down, H up. Okay. If we number those carbons, 1, 2, 3, 4. Again, there's where the 2 comes from. Double bond starts at carbon 2. Okay. The difference here the difference between cis and trans all comes about with the direction, the relative direction that the carbon groups are coming off of that double bond. Okay? So cis means the same. Okay? Cis and trans used to be prefixes that nobody has ever heard of. Now they actually are used quite a bit involving gender identity and things like that. So a lot of people are actually more familiar with these terms now. It's good for chemistry, I guess. But trans means opposite, right? So instead of having the CH3 go the same direction down here, they're going to be in opposite directions, like that. Okay? That's trans. This same direction. The reason we weren't concerned about direction at all before with single bonds is that single bonds freely rotate. Okay? We're going to be using model kits in lab, and you'll be able to see how anything that's single bonded, you can twirl that single bond around and it can go whatever direction we want. But once we have a double bond, because that pi bond extends above and below the plane, that locks it in place. So there's no rotation around a pi bond. So that's why this compound is totally different, pretty much, from this compound. Okay? Even though they're just sort of different in direction, those two molecules will have different properties, and you'll be able to separate them and have them in different bottles and everything. Okay? So we need to use cis and trans anytime we have carbon groups attached to both of the double bonded carbons. Okay? We do not need cis and trans, for instance, for propene, because we only have carbon groups attached to one side of this double bond. Okay? And we don't need any cis or trans for butene, because again, only carbon groups are attached to one side. Okay? But as soon as we get a double bond in the interior of a molecule, it can either be cis or trans. And then alkynes. Oh, actually here, we have to do this example here before we do alkynes. This is a branched alkene. Okay? It's a double bond, but we got all kinds of branches. The key here is that you have to number now from the end closest to the double bond. When we have double bonds, that's sort of taken over priority as the most important feature of the molecule. Okay? So regardless of where the branches are, we're going to number this backbone from the end that's closest to the double bond, okay? And then the backbone must contain both double bonded carbons. Okay, so on this one, either one of these could be carbon number 1. Okay? Those are symmetrical. Those will give us the same result. Okay? But let's just pick one of them. And either one of those could be number 5. But I'm definitely going to number starting from this end, not this end. Okay? Even if there was no branch there. I like doing that as sort of an example. that structure would still be 1, 2, 3, 4, 5. Okay. Okay. But this one right here, what would its name start with? I think. Start with the branches, or like we did before. What would the branches be on that one? Mm-hmm. Yep. Because you got a backbone here, right? Got branches, just like that, right? Those are CH3s. So how would you start that name? Let's do it up here. 2, 4. 2, 4 what? 2, 4 methyl? We have to say that there are two methyls. Yep. But 2, 4 dimethyl. Okay. 2, 4 dimethyl. Then what? We have this double bond in here, though. So it's going to be pentene. But remember, we also have to say where that double bond starts. Yep. 2 pentene. Without any of those branches, it would just be 2-pentene, right? With the branches, those branches just go on the beginning of the name, 2,4-dimethyl, 2-pentene. What would the bottom one start with? 4-methyl? 4-methyl. Yep, 2-pentene. Okay. That makes sense? So we can add branches to anything. Okay. One way of thinking of it is just kind of starting by, you could even start by ignoring the branches. Okay. If you just ignored those methyl groups, then you've got 2-pentene. Okay. But those methyl groups can be attached, or ethyl or isopropyl or whatever. Those can be attached, sort of anywhere in the molecule. But that just gets put on at the beginning of the name. So, what do alkynes have? Yeah. So, ethine is F is 2 carbons. Meth, eth, prop, but. Okay. 2 triple bonded carbons that each have how many H's then? Yeah, let's just put 1 H on each of them. And I'm going to draw that linear, because we talked about how the triple bonded carbon has 2 electron groups. Right? It's really just 2 sigma bonds going out 180 degrees from each other. And then now 2 pi bonds to make the triple bond. So that's ethine. Acetylene is the common name for that. So it's used. It's a high temperature welding fuel, right? An acetylene torch is a very high temperature, but ethine is the IUPAC standardized name for it. Okay. So 1-butene. 1-butene. There are essentially 3 parts of that name, right? There's 3 pieces of information contained in that name, right? And let's start at the back. What does the yne, Y-N-E, mean? Triple bond, okay. What does the but mean? Meth, eth, prop, but, right? What did somebody tell me once? Mary eats peanut butter. Okay. Meth-eth-prop-bute. I'm sure you could think of a much more interesting, much less appropriate mnemonic to remember those. So 4 carbons. There's a triple bond, and what does this number 1 mean? That's where, yeah, the triple bond starts at the first carbon. So let's do HC, okay? And then no H's on that one. And then got carbon 3 and carbon 4. How many H's would be on carbon 3 here? Yep, so let's call that CH2. And then carbon 4, CH. Yeah, so, yep, so there's 1 butane. 2 butane is the same except, yep, starts at 2. It's between 2 and 3. So, you know, a lot of times it's easiest just to draw those C's. Let's make the triple bond there. Okay, something like that. And I got N carbon, CH3, and then CH3. Okay. So, anybody have any questions? You can have branches in triple bonded compounds just as well. The only issue is the branch cannot come off of the triple bonded carbon, right? Because triple bonds only leave 1 more bond. But the other part of the molecule can have as many branches as we want. There are molecules that have multiple triple bonds, multiple double bonds, double and triple bonds. There are rules of thumb for naming all kinds of things like that. All we need to focus on is just a simple 1 double bond or 1 triple bond, okay? But it could have as many branches as we need. Okay? All right. Let's just introduce ourselves to this sort of last group of aromatic hydrocarbons. Alkanes, alkenes, alkynes were just sort of regular hydrocarbons. But aromatic hydrocarbons are sort of special because they have this benzene structure in them. Benzene, the molecule benzene is C6H6. It's an organic compound that's extra stable. And you'll notice from its formula, it's a very unusual formula. It is the same number of H's as carbons, a very low proportion of H's to carbons compared with the other hydrocarbons, right? We've made a ring, okay? But it's not the ring that makes benzene stable. The really interesting thing is that it is alternating single and double bonds through that ring of 6 carbons, and there are 2 identical resonance structures. Okay? So at the end of first semester, we usually have a discussion about how a resonance structure is not like an actual thing. Okay? The whole molecule is the combination of all possible resonance structures. Okay, that you can draw from it. And it's not like it's switching back and forth. It's that all the resonance structures get blurred together to make the real molecule. Okay? So when we draw individual resonance structures of benzene, we're just sort of showing half of the actual structure. And you know, we've done like we did before. Sometimes we put big square brackets around it to show that those are just 2 ways of drawing the same molecule. Okay? But you'll see because we have alternating double and single bonds in there around the ring. That's why each carbon only has 1 H, because they're essentially trigonal planar. Okay? Double and single, like that. Okay? The true structure is a hybrid of those resonance structures. The CC bonds are all identical in a benzene ring. Okay? The lengths of those CC bonds are halfway between a normal single and double bond. Okay? So it's a true hybrid. There's no asymmetry to it. And you know, that's why sometimes benzene is drawn as a line structure with this circle in the middle. It's not typically how we'll do it. Okay? We will typically just pick one of the resonance structures to draw as a line structure. So we'll very commonly do something like that, just as a reminder that we're actually dealing with. What was that? Does that mean it's time to quit? I don't know. Anyway, let me just show you this little picture here. Remember how a pi bond... God, that was weird. Okay. So to make a double bond, we have a sigma that goes in between, and then the pi bond sort of extends above and below. Like that. So one pi bond, okay, and that's what makes a double bond. So when we have those two resonance structures, what actually happens is the pi bonds extend above and below as an entire ring. Okay? So you've got an entire ring of pi bonding happening above and below that structure, okay? Which is sort of what makes it extra stable. And this benzene structure actually shows up in several natural compounds. At the start of next time, I'll show you some structures, and we'll deal with actually naming aromatic hydrocarbons. But that's our little introduction to that. Okay. So I guess they still have some more work to do on the AV in this room. I thought I was cautiously optimistic that they had made some improvements. But anyway.